in the last class we just started the discussion on dynamic behavior of first order system, that we will continue. So, the topic is dynamic behavior for first order process introducing step change in input variable. So, we know the first order system can be represented by the first order differential equation, and we have considered this equation previously. A naught y equal to b f t. This is the model of a first order process, and transfer function we got, that is G s equal to y bar s divided by f bar s equal to k p divided by tau p s plus 1, and we have considered step change in input variable with magnitude a. I mean f t equals to a, and in Laplace domain this is a by s. So, y bar s becomes k p a divided by s tau p s plus 1. Inverting this, we get y t equal to a k p 1 minus exponential of minus t divided by tau p. Up to this we had discussed in the last class. Now, we will try to plot the y versus time. Fine. So, to plot this equation, I mean we will make the plot in terms of dimensionless quantities. So, dimensionless quantities means we will consider y t divided by a k p versus t divided by tau p. We will make a plot between y t divided by a k p versus t divided by tau p. This is the dimensionless quantity which we will consider along y axis, and this is also the dimensionless quantity which we will consider along x axis. So, what will be the plot? Y t divided by a k p and t divided by tau p. See, we are introducing a step change with magnitude a. So, what will be the final steady state? Final steady state we can find considering t tends to infinity. So, if we consider y t divided by a k p with t tends to infinity, how much it is? 1. So, final steady state value is 1. Fine, and this is the starting state. I mean t time equals to 0 is the starting point. Now, the dynamics of yt is represented graphically by this curve. Fine. So, this is the dynamic response of the first order system if we introduce a step change in the input variable with magnitude f, magnitude a. Now, we will note down few points. We will note down few points. This is basically a self regulating process. Fine. This is a self regulating process. Self regulating process. Previously, we have considered one case, that is pure capacitive process, and that is non self regulating process. If we take one example, then I think it will be clear why this is self regulating process. We can consider a liquid tank system. Input is Fi, output is F, height is h. So, if Fi increases, then what happens? Height increases, fine. Then hydrostatic pressure increases, which in turn increases the outflow rate, fine. And after a time period, an equilibrium is established. After a time period, an equilibrium is established, and at that equilibrium state, the value of yt by AKP is the new steady state value. That is the reason for which we are considering this is the self regulating process. This is the first remark. Second remark, what is the slope of this response at time t equal to 0? Can you calculate the slope at time t equals to 0? I mean d yt divided by AKP d t by tau p at time t equals 0. How much is this? Exponential of minus t by tau p at t equals 0. So, slope is 1, fine. So, slope is 1. If we see this dynamic response, then this state line has the slope of 1. What will be the corresponding t by tau p value? If slope is 1, what is the corresponding t by tau p value? 1, because this value is 1. So, it is 1, fine. So, can we say that if the initial rate of change of yt were to be maintained, the response would reach its final steady state value in one time constant? Can we say if this is 1, that means t by tau p 1, that means t equal to tau p. So, we can conclude that if the initial rate of change of y t were to be maintained, then the response would reach its final value in one time constant, because t divided by tau p is 1. So, obviously, t equal to tau p. This is the second remark. Fine. Next, we will go for the third remark. But what happens originally? I mean, if we see this plot, if this is the response, then only the final steady state value we obtain at t equal to tau p, but that is not the original case. The dynamic response is this one. So, at t equal to tau p, how much is the y t by a k p value? Can we calculate that? See, we have the equation y t divided by a k p equal to 1 minus exponential of minus t divided by tau p. Considering t divided by tau p equals 1, we get y t divided by k p equals 0.632. Fine. Considering t by tau p equals 1, we get y t divided by a k p 0.632. That means, originally the process reaches 63.2% of its final value. So, this is 0.632. Originally, in one time constant, the process reaches 63.2% of its final value. So, we can write in this tabular form that when t equals tau p, this value is 0.632. Similarly, if considering 2 tau p and using this equation, we get 0.865. I mean, in the 2 time constants, the process reaches 86.5% of the final. Similarly, if we consider 3 tau p, we will get 0.95, 4 tau p, this is 0.98. Fine. This is our third remark. Fourth remark. We discussed one thing, that the gain equals change in output divided by change in input. Recall this correlation which we discussed earlier. Gain equals change in output divided by change in input. So, for this system, what is the change in output? What is the change in y? That is Kp multiplied by A, because we have seen earlier that considering t tends to infinity, y t divided by A K P equals 1. That means y equals A K P, and how much change we introduced in the input, that is A. So, this gain becomes K P, and originally we have considered in the transfer function K P as the gain, but remember that this is a steady state gain, fine, and this is we determined considering steady state only. So, these are the 4 comments we can make on the dynamics of first order system considering step change in input variable with magnitude A. Fine. Our next topic is variable time constant. Tau p and gain K p. So far we have discussed considering time constant and gain as constant quantities. Now we will consider one case in which we will observe that tau p and K p are not constants, fine. So far we have considered tau p and K p both are constants. Now we consider one example and we will observe that these two are variables. We will consider one that simple liquid tank system. Input flow rate is F I and output flow rate is F. Suppose F is proportional to square root of liquid height. So, F equals alpha root h, fine. We derived the modeling equation for this system considering F equals alpha root h. I am writing that modeling equation which we derived earlier. F I, fine. Then in this equation, this is the nonlinear term, we linearized it considering Taylor series, and finally we got if dH dt plus alpha divided by 2 root hs h equals F I. We got this equation in linearized form, and considering the deviation variables, we can write this equation in this form: A dH prime dt plus alpha divided by 2 root hs h prime equals to F I prime. Now, we can represent this equation introducing tau p and K p by this form: tau p dH prime dt plus h prime equals Kp A phi prime. Fine. Now, here tau p equals 2 a root over of H s divided by alpha. If we compare these two equations, we get the expression for tau p equals 2 a root over H s divided by alpha. Similarly, we get the expression for Kp, that is Kp equals 2 root over H s divided by alpha. So, this is the expression for time constant and this is the expression for gain. Are they constant or variable? See, for a particular Fi value, suppose that is Fi is 1, we get the corresponding height, that is suppose H is 1. Fine. Now, if we change this Fi value to Fi is 2, we get different height, that is suppose H is 2. Fine. That means, we can conclude that this H s varies depending on the Fis value, the H s is obtained. So, we can say that this tau p and Kp both are not constants in this particular example, they are the variables. Fine. So, this is all about the dynamics of first order systems. In the next, you will discuss the dynamics of second order systems. So, next topic is the dynamics of second order systems. What is the definition of second order system? What is second order system? Second order system is one whose output y is modeled by the second order differential equation. Second order system is one whose output y is modeled by the second order differential equation. So, the output is y t and this should be modeled by second order differential equation. Fine. Now, we will consider a second order differential equation. So, for the second order process, the modeling equation we can represent by this form: A2 d2y dt square plus A1 dy dt plus A naught y equals b f t. Fine. A, B both are constant coefficients. A, B both are constant coefficients. Y is the output of the process, F is the input to the process. Fine. Y is the output of the process and f is the input to the process. Now, if we divide both sides of this equation by A naught, we get A 2 divided by A naught d 2 y dt square plus A 1 divided by A naught dy dt plus y equals b by A naught f t. Fine. This equation we get by dividing both sides by A naught. Now, we will represent this equation by this form: tau square d 2 y dt square plus 2 zeta tau dy dt plus y equals k p f t. We will represent this equation, the previous equation, in this form: tau square d 2 y dt square plus 2 zeta tau dy dt plus y equals k p f t. Here tau square equals A 2 by A naught, tau square equals A 2 by A naught, 2 zeta tau equals A 1 by A naught, and K p is b by A naught. Fine. K p is b by A naught. This tau is called natural period of oscillation of the system. Tau is the natural period of oscillation of the system, and zeta is here damping factor. Zeta is called damping factor. Fine. And K p is the steady state gain or static gain. K p is the steady state gain or static gain. Fine. Considering y and f both are deviation variables, we finally get the transfer function of this second order system taking Laplace transform of this equation. Considering y and f both are as deviation variables, we get the transfer function of this second order system with taking Laplace transform of this equation as G s equals y bar s divided by f bar s equals K p divided by tau square a square plus 2 zeta tau s plus 1. Fine. This is the transfer function of the second order system. Second order system. Now, this second order system transfer function includes one term, that is damping factor. Damping factor provides a measure of the amount of damping in the system. Damping factor provides a measure of the amount of damping in the system, that is the degree of oscillation in a process response after a perturbation. Damping factor provides a measure of the amount of damping in the system, that is the degree of oscillation in a process response after a perturbation. Fine. Now, small value of zeta, what it indicates? Small value of zeta means little damping. Small value of zeta implies little damping, but a large amount of oscillations. But a large amount of oscillation. Fine. Suppose this is the output and the response we are getting in this way. Another response is like this. So, in this case we can say large damping. In the second case, small damping. Fine. When the damping factor zeta becomes 0, when the damping factor zeta becomes 0, when zeta equals 0, in that case the oscillation occurs with constant amplitude. So, zeta becomes 0 belongs to undamped system. It means oscillation with constant amplitude. For the case of undamped system, we observe oscillations with constant amplitude. In another case, we consider zeta less than 0. What it indicates? Oscillations with increasing amplitude. So, it belongs to unstable system. It belongs to unstable system. For this case, the output is somewhat like this. Fine. So, for all stable systems, zeta should be greater than 0. for all stable systems zeta should be greater than 0. Fine. Now, earlier we have considered first order systems. Presently, we are discussing the second order systems. Now, what processes are called second order systems? So, we will discuss now the systems with second or higher order dynamics. How we can obtain the second or higher order dynamics, that we will discuss now. If two or more first order systems are connected in series, then we obtain second or higher order systems. If two first order systems are connected in series, the overall dynamics is second order dynamics. If we connect more than two first order systems in series, we obtain higher order dynamics. Fine. So, this is the first option. I mean, by this way we can get the higher order dynamics. So, under this category, the processes consist of two or more capacities. And they are first order systems in series. Fine. If a process incorporates a controller, then also we can obtain higher order dynamics. Say for example, we have a first order system. We have a first order system. If one controller is employed with this first order system, then the overall response may be second order response. If a process includes a controller, then we can obtain second or higher order dynamics, and this is the example. If we consider a first order system that includes a controller, then the overall response may be second order dynamics. Fine. Thirdly, few processes are inherently higher order. Few processes are inherently second order systems, but this is very rare in chemical engineering. Fine. And we will not discuss this third option. We will discuss only first and second options. Fine. Okay. Now, we will discuss the types of second order system response. Previously we have obtained the transfer function for the second order system in general form, that is Gs equals Kp divided by tau square A square to zeta tau s plus 1. This transfer function we derived earlier for the second order system. Fine. Now we want to determine the poles of the second order system. For determining the poles of the transfer function, we write tau square A square plus 2 zeta tau s plus 1 equals 0. Fine. For determining the poles of the transfer function or poles of the system, we write tau square A square plus 2 zeta tau s plus 1 equals 0. So, if we represent the pole by P, then P equals minus 2 zeta tau plus minus root over 2 zeta tau whole square minus 4 tau square divided by 2 tau square. See, this is the quadratic equation. So, we can easily obtain the poles. We have represented the poles by P, and the expression for P is this one. So, we will get basically two poles, P1 equals minus zeta divided by tau plus root over of zeta square minus 1 divided by tau. Another pole is P2, and P2 equals minus zeta divided by tau minus root over of zeta square minus 1 divided by tau. Fine, these are the two poles. Now, we will categorize the system response based on the value of zeta. We will now categorize the system response based on the value of zeta. So, first we will consider zeta greater than 1. In case 1, we will consider zeta greater than 1. Fine. If zeta greater than 1, then we obtain two distinct real poles. You see from the expressions of P1 and P2, if we consider zeta greater than 1, we get two distinct real poles. Fine. The corresponding system response is called overdamped response. The corresponding system response is called overdamped response. This is case 1 where we have considered damping factor greater than 1, and damping factor greater than 1 implies two distinct real poles. In the next case, we will consider zeta equals 1. So, what about the poles? Two equal real poles, I mean you can say one pole. So, we can write two equal real poles. It means one real pole, and that is minus zeta divided by tau. We obtain for the case of zeta equals 1 a single real pole, and that is minus zeta divided by tau. Then the corresponding system response is called critically damped response. Critically damped response. So, when zeta equals 1, the response is critically damped. Fine. In third case, we will consider 0 less than zeta less than 1. In the third case, we consider zeta is in between 0 and 1. In this case, what about the poles? We get two complex conjugate poles. We get two complex conjugate poles, and the poles are P1, one is P1 and another one is P2. The expression for P1 is this one. P1 equals minus zeta by tau plus I root over 1 minus zeta square divided by tau. Another pole is minus zeta by tau minus I root over 1 minus zeta square divided by tau. So, when zeta is in between 0 and 1, the corresponding response is called underdamped response. So, this is the underdamped response. So, these are three different cases depending on the value of zeta. Fine. Fine. Now, we need to take the inverse of Laplace transform to obtain the expression for y in time domain. That we will discuss in the next class. Fine. The expressions for y in time domain. Thank you. What you were saying? Yeah, that I will correct.